Hello everyone, this is the problem on spur gear design. So you can see the question here: design a pair of spur gear to transmit 20 kilonewton at a pinion speed of 1440 rpm. The transmission ratio is 4. Assume suitable material and stresses. Actually, for calculating the design procedure of a spur gear, these four conditions are enough. Okay, power, speed and transmission ratio. Here in the question he has given us transmission ratio, although if he has given like a velocity ratio or gear ratio, that means it is nothing but I. Okay, I is equal to 4. Okay, so you can take the value directly. Okay, so next he has mentioned us to calculate the design procedure with suitable material and stresses. So we are going to select suitable material and stresses that are helpful for design of a spur gear. Okay, so the first thing that we need to do is we need to write the given data. The power given, he has given us power to be transmitted as power to be transmitted, that is equal to 20 kilonewtons, that is 20,000 newtons. Next he has given us pinion speed. Pinion speed he has given, that is n1, that is equal to 1440 rpm. Okay, we have got the transmission ratio, that is I is equal to 4. With this we can find the gear speed. Okay, that is pinion speed is there, so transmission ratio is there, so with that we can find the gear speed. So the gear speed is equal to, that is n2 is equal to n1 by I, that is 1440 by 4. You can get an answer of 350 rpm. So this is the thing. So the first step that we need to do is we need to select the material. So proper selection of material is very important. So the proper selection of material can be found out in the page number. So you can find the data related to spur gears in chapter number 28. So where you can find the data related to spur gear in chapter number 28. Later you can select the suitable material from page number 28.13 in tabular column 28.4. Here you can find the design stresses for gear material, and the gear materials are here, where the cast iron are used for low loading conditions, and C45 are used for medium loading conditions, and steel, these are steel, so steel will be used for high loading condition, and C45 will be carbon 45 percentage will be, you can use it for medium grade steels. So as we know that the pinion will be like this and gear will be like this. So the smallest one will be the pinion and largest one will be the gear. So as the pinion will be facing more loading condition rather than the gear, we have to select high strength material for pinion and low strength material for gear, or otherwise we have other conditions also, like if in the question itself they have mentioned the life of a gear means, we have to do the procedure in a different manner. So we are going to design a gear where life is not given. If the life is given means we have to select the material based on the life conditions. Okay, so you can select both pinion and gear materials will be same under some conditions that we will see in the next question. Now we are going to design a gear based on without any life conditions. Okay, so here you can we are going to select a material, that is C45, that will be a medium loading condition, and this will be high loading conditions. If you select the C45 for gear and you have to select the this material for nickel and chromium for pinion. Okay, so because it is having high strength. Okay, so if you select C45 for pinion, then you have to select the material grade 35 like that for gears. Okay, so you have to choose the highest material, or else there is a chance of selecting both the similar materials that we will discuss in the next coming question. Okay, so the step number one will be material selection. So I have selected the pinion material as nickel and chromium. So the heat treatment process also plays an important role that we will see in how it plays a major role. So if it is a carburized one, we'll be taking the material will be different one, like if it is a carburized one, we will be taking the surface hardness more than 350. If it is not carburized, means we can take less than 350. Okay, based on the heat treatment process also, we have some important role. Okay, so from here we can get the design stress, that is surface stress and bending stress. Okay, so the sigma C and sigma B. Okay, so sigma C will be 950 and this will be 320, and gear material C45, that is sigma B will be 140 and sigma C will be 500. Okay, so with this we have completed the material selection, that is the first step in the design procedure. So the next thing that we have to do is we have to find the center distance, that is minimum center distance. Okay, so we have to find the minimum center distance. Okay, so for finding the minimum center distance, you have to go for the page number 28.14. Okay, so you can find the data related to spur and helical gears. Okay, as we are having the syllabus point of view, with respect to syllabus point of view, we are having only spur and helical gears. If you go for PSG data book, means you can find the spur, helical as well as bevel gear data also. Okay, so you can take the formula as this is the center distance between pinion and gear. You can use this formula. Okay, just use that formula to find out the center distance. Step 2, finding center distance. Okay, I plus 1 root over 3 into 0.74 So this is the formula we are having in the data book. So where I is nothing but your transmission ratio that we have already got in the question itself, and sigma C. So sigma C is your crushing stress that can be found out from the data here, that is taken from the material selection itself. Okay, so remember to keep the brackets. So brackets indicates the design value. Okay, so without brackets means that is the calculated value. So the calculated value is different from the design value. That means you are going to calculate the values, okay, in according to the design values. So let me explain it later. So first thing that we are having is design value. Okay, design crushing stress. that we can take it from the material selection, and mt is nothing but your twisting moment or twisting torque. Okay, psi value. So psi value that can be found out in the data book itself, and all the things can be found out in the data book. Let us go stepwise. So the first thing that I am going to take is uh, I is nothing but 4 plus 1 root over 3, 0.74 square sigma c. So sigma c that I am taking as 500. Why I am taking the minimum value? Why not the highest value? If you design a material for the weaker one, that means less strength value one, less strength material, automatically the high strength material will be in a safe position. Okay, so if you design the material for a less strength, if you design the procedure, so or if you design a procedure for a less strength material, means obviously the material having high strength will be in a safe position. Okay, so that's why I am going to design the procedure for a less strength material. Okay, later. Okay, later we are going to calculate the e value, so the Young's modulus value. So the Young's modulus value can be found out from the page number 28.17. So the 28.17, you can find the equivalent Young's modulus from the formula here. Okay, so both nickel and chromium will comes under steel itself. That's why we are going to take the value of 2.15 into 10 to the power of 6. So that is in kgf per centimeter square. So after conversion we can get the value of around 2.15. E value is equal to 2.15 into 10 to the power of 5 Newton per mm square. Okay, so this is the value that I have got. So later we have to calculate the twisting moment. So so here you can find the in page number 28.15, you can find the table 28.16. You can find the formula for design twisting moment. If it is in brackets, means that is the design value, and if it is not there, means it is the calculated value. Suppose the calculated value is 50 and kd into k will be some 2, and we will be going to design the material for 100. Right, did you understand how it comes? So the calculated value, this is the design value. Okay, so we are going to do the calculation for this design value. Okay, so the design value must be higher than the calculated value. Okay, so mt is nothing but your nominal twisting moment. So the formula is mt into kd into k. So kd into k. So here spur gear and helical gear comes under the symmetrical sections. Unsymmetrical and overhanging scheme will be like bevel gears and all. Okay, so all the you can get the you can take the value as 1.3 kd into k, and mt can be found out from the formula here, 60p by 2 pi n. Okay, mt is equal to 60 into 20,000 by 2 pi n value 1440. Okay, so you can find the value of mt. Okay, so after finding the value of nominal twisting moment, you can substitute the value in this format, and you can find the design twisting moment. So let me calculate. So I have got an answer of 136.4 into 10 to the power of 3 Newton mm. Okay, so I will be multiplying into the power of 1.3. So I will be getting a design torque will be design twisting moment will be I will be getting 177.3 into 10 to the power of 3 Newton mm. Okay, so this is the value that I have got. After getting the values of empty, you can substitute the values here into 2.15 into 10 to the power of 5 into 177.3 into 10 to the power of 3 by I value will be 4 into psi value. So where you can find the psi value means, so you can find the psi value in this page number 28.17. You can find out in the table number 28.10. Okay, so open type 0.1 to 0.3. Just remember psi value is equal to b by a. Okay, phase width by center distance. Okay, so 0.1 to 0.3. For high speed we will be taking up to 0.3. so always we have to take, if it is not given in the question means we have to take the value as 0.3. okay, into 0.3. just substitute the value and you can find the answer. So I have got the answer. The design center distance value will be, I have got an answer of 206 mm. Okay, 206 mm. Okay, so this is the value that I have got. Later we have to find out the minimum module. So minimum module required based on the beam strength that will be given in the page number. So in the page number 28.14 you can find the formula for module. That is, module means pitch diameter by number of teeth. Okay, so pitch diameter by number of teeth, module value can be found out. For spur gears you can find the formula, and helical gear also you can find the formulas. So just substitute that formula and you can find the value of module. Okay, so the step 3 will be minimum module. So the minimum module can be found out by this formula. (1.26 root over 3 design twisting moment by y into z1. Okay, so this is the formula. So we are going to see you stepwise. So we will be substituting the values one by one. 1.26 root over 3 empty value, that is 177.3 into 10 to the power of 3 by y value. So what is meant by y value here? That is your form factor value. So see here, so in the page number So in the page number 28.19, table number 28.13, you can find the form factor value, that is y value. So that will be based on the z value, so number of teeth. So here from teeth of 16 to 24 you can find it, that is will be the medium loading condition, and 12 to 14 will be high loading condition, and 12 to 14 will be the low loading conditions, and above 26 and all you can find it for high loading conditions. Okay, so we have to choose, we have to go for an assumption case of here only. So we have to select the teeth that will be between 16 to 24 only. Okay, so how can we choose? So here 20 teeth is there, so how can we choose the value? So we are having plus minus and all thing. What are those things? So we are going for an addendum modification. So addendum modification means while you are going for a meshing condition, like two teeth, gear and pinion are going to mesh with each other, at that point of time we have to go for a slight modification of the addendum value. So that modification will lies either plus or minus. So we whereas x value won't change, okay, 0 value won't change. That's why, so if you go for an assumption case of 20 means 0.389, so this value must be taken, okay. So I have selected the y value as 0.389 and sigma b value. So sigma b value will be 140. I am going to take the minimum value, okay. 140 into teeth, I have taken psi m value. So psi m value will be, so see here in the page number 28.18, in the table column 28.11, you can find the value of psi m. So the psi m value is equal to 10 for general condition, okay. So just substitute that value 10, okay. So after that you can find the value of module here, okay. So after calculation I have got an answer of 3.2 mm, okay. So this is the module that I have got, but in the page number 28.20 you can find the recommended series of modules. So here you can see the preferable one. So see here, so always preferable is to be taken to the use of modules started in the column 1. Modules given in the bracket of column 3 should be avoided as far as possible, okay. So we have to go for a preferable value. So here we are having 3 and we are having 4. We have got an answer of 3.2, so that won't be suggested. So just go for the value of preferable one, that is 4, okay. So next we have to go for the calculation of face pitch circle diameter. So before calculation of pitch circle diameter, we have to calculate the corrected number of teeth, okay. So the corrected number of teeth can be calculated by the formula here, see here. So number of teeth can be found out by z1 is equal to 2a by m into I plus 1, okay. So this is the formula we are having. z1 is equal to 2a by m into I plus 1, okay. So 2 into a value, so a value that I have got is 206 by m value that I have got is 4 plus 1. So I will be getting an answer of 20.6, okay. So z1 value, so that means almost we will be going for z1 is equal to 22, okay. So because why I am going for 22 means, so see here, so here in the teeth value you don't have 21, so that's why I'm going for 22, okay. So later we are, for calculation of z2, so we are having a formula z2 is equal to iz1, that is in the page number 28.27 in 28.27 table column. Z2 is equal to iz1, so 4 into 22, so we will be getting 88 teeth, that will be on gear, okay. 88 teeth, okay. So this is the formula. So the fourth step will be the pitch circle diameter. Step 4. Pitch circle diameter, okay. So the pitch circle diameter can be found out by the formula d1 is equal to mz1, that will be found out in 28.27. d1 is equal to mz1, okay. d1 is equal to mz1 and d2 is equal to mz2, okay. So m is nothing but 4 and 22, 4 into 88, So the pitch circle diameter for pinion will be 88 mm and gear will be 352 mm. Okay, so after that we have to calculate the corrected center distance. Why we are going for a corrected center distance means we have gone for an assumption values before that. So corrected center distance can be found out. So from the page number 28.27 you can find the corrected center distance formula. So A is equal to m into z1 plus z2 by 2. Okay, so we have to correct the center distance. Corrected center distance. Okay, corrected center distance is equal to m into z1 plus z2 by 2. So 4 into 22 plus 88 by 2. So I will be getting an answer of 220. So since the corrected center distance is more than the calculated distance, okay, so we have got an answer of a value is 206. So since the value is more than whatever the corrected center distance is more than the calculated value, so that's why our design will be safe. If it is less than means we have to change the module. Okay, if you got us to 200 or something, so then we have to change the module value. Okay, so then your design is not safe. That's why we have to change the module. Then you have to prefer a higher module, that is 6 or something. Okay, if again it makes some confusion means if the value is again less than the previous whatever the calculated value, then we have to go for higher, that is 8. Up to 8 you can change the module, but after 8 you should not change the module value. Then we have to change the teeth value. Okay, so the teeth is, we have assumed it as 21st, so we have to go for an assumption case of more than 20 or 24 28 like that. Okay, so if the whatever the corrected center distance is more than the calculated distance means then the design is safe. If it is less than means then the design won't be safe. Okay, remember that thing. So next thing that we have to do is we have to calculate the face width. So face width can be calculated by a formula psi is equal to b by a. So face width is nothing but b. Okay, b is equal to psi into a. Okay, psi value that we have already assumed. Another formula is also there, that is b is equal to psi into m. Okay, so these are the two formulas that we are having that can be found out. So see here, so psi m is equal to b by m. So b is nothing but your face width, that can be found out by 28.18. So already psi m value we have assumed as 10 and m value we have already known. So with that we can find the b value, or else we have to go for psi is equal to b by a. So already we are having a value and psi value we have assumed as 0.3. Okay, just do the calculation. After calculation we have to take the highest value. Okay, so b is equal to 0.3 into a value, corrected distance. Okay, so b is equal to psi m, that is 10 into 4. So we have got an answer of 66 and that is 40. Later we have to calculate the corrected torque. Okay, design torque. Okay, so mt is, design torque is equal to mt into kd into k. So we have empty that we have calculated earlier, so we have to keep the empty as it is, and kd and k, these two values will be taken from the tabular columns. How we have to take and where, from where we have to take, that we will see it now. So the empty value that I have already calculated is 136.4 into 10 to the power of 3. Okay, so the kd and k value, so k is nothing but your load concentration factor, that is k for steel gears, quality number 8, having a hardness number greater than 350, and kd is nothing but your dynamic load factor, that is in the page number 28.16. so you can find the values. So see here, so see here, so sigma p is equal to face width by pitch circle diameter. So pitch circle diameter of pinion. Okay, so b is nothing but your face width. So face width with that we have taken is 66, that is the highest value, and d1 is nothing but your pitch circle diameter of pinion, that is 88. Okay, b by d1, 66 by 88, so I have got an answer of 0.75. okay, so 0.75, so you have got an answer here 0.8 something. So we'll be taking as a bearing screw, gears and symmetrical section. We don't go for here, so eccentrical section means we'll be going for like bevel gears and all. So those we won't take. Only symmetrical gears means that is helical and spur gears, we have to take the values from here only. So I have got an answer of 0.75. so obviously I will be taking the value like this. I will be taking as 1.05. okay, so the k value is 1.05. okay, next we have to calculate the kd value. So the kd value can be found out by, so see here, so cylindrical one, conical means bevel gears and all. So cylindrical one, so 5 is nothing but your low loading conditions, 6 and 8 will be the medium loading, and 10 will be the high loading conditions. So either we have to take for 6 or 8. So I will be taking, so based on the hardness, so based on the type of heat treatment, carburizing or type, that we will have to take the greater than or less than. So if it is a carburized one, we have to go for greater than 350. So I will be taking, so see here, so you can find the quality is number as 8 having greater than 350. So that's why I am taking as 8 greater than 350. I will be taking based on the pitch line velocity. So pitch line velocity can be found out by formula v is equal to pi d n1 by 60 into 1000. okay, so that we have to do. So here pitch line velocity v is equal to pi into d1 into n1 by 60 into 1000. okay, so pi into d1 is 88 into n1 is 1400 by 60 into 1000. So I have got an answer of 6.45 meters per second. So based on the pitch line velocity and hardness number and cylindrical gear type, we have to take the value. So I have got an answer. So pitch line velocity is C here 1.0, 3.0, but the value that I have got is 6.45. okay, so that is almost near to 8.0. so I am taking the value as 1.4. so that is greater than 350. okay, hardness number and 8. okay, so you can take the 6 value also. okay, either 6 or 8, and you can prefer any of the one. okay, so I am preferring for 8. okay, So that is 8 will be the high loading, that is the coarse one. Okay, that means high machineries. Okay, so whereas 6 and 8 will be the medium one, and 5 will be the low one. Okay, uh, okay, so I am taking the KD value as 1.4. Okay, now we are going to substitute all those values to find the corrected twisting torque. Okay, so our modified twisting torque, so 136.4 into 10 to the power of 3 into 1.05 into 1.4. Okay, so this is the value. So we have to check the value, and we have got an answer of 200.5 into 10 to the power of 3 Newton mm. Okay, check the value once and tell me if any corrections are required. Okay, so next step is to find the checking the induced compressive stress and bending stress. So induced compressive stress and bending stress can be calculated from the page number 28.14. You can find two different formulas, that is compressive stress and bending stress. So the induced compressive stress sigma c is equal to 0.74 I plus or minus 1. So plus is nothing for external gearing and minus for internal gearing. Okay, remember that one also. IB MT. So whatever the value, that is induced compressive stress, must be less than or equal to design stress. Okay, design crushing stress. Okay, so I value that we have already known, that is 4 plus 1 by A value, that is corrected one, 220. Okay, root over 4 plus 1 by 4 into, so the B value will be, so the B value will be 66 into E value 2.15 into 10 to the power of 5 into MT value, that is changed value. Okay, 200.5 into 10 to the power of 3. Okay, so we have to do the calculation and just tell me the answer. So whatever the value that we have got must be less than the designed value. So I have got an answer of 480 Newton per mm square. Newton per mm square, which is less than the designed value. So see here. So the designed value is 500. So I have got an answer of 480. If you got more than 480 means, that is more than 500 means, then your design is not safe. Okay, so then you have to redo the calculation, or else if you don't have time in the examination, just write it out. I will be modifying the m value and or else number of teeth value in order to get the design in a safe mode. Okay, just write that statement so that you will be in a safe hands. Okay, so next we have to go for calculation of sigma b. So the sigma b can be found out by I plus 1 by a into m into b into y into mt grant sigma b. Okay, less than, so 4 plus 1 by a value 220 into 4 into 66 into y value. So here the y value must be taken from the So see here, so the number of teeth that we have got is 22, so that's why I'm using 0.402. okay, 0.402. okay, so after calculation we will be getting the induced bending stress. okay, so form factor value will be corresponding, so the y value will be corresponding to the number of teeth, that is corrected number of teeth that we have calculated earlier. okay, 1 minute, let me show you. So see here, so corrected number of teeth is z1 is equal to 22. okay, so I have got an answer of 43 Newton per mm square. okay, so 43 Newton per mm square, so which is less than 140, so our design is safe. So next we have to calculate the other parameters. So what are the other parameters? That is, whatever the terminology and whatever the nomenclature that I have said, that all we have to calculate. okay, 1 minute. So last step is other parameters, calculation of other parameters. So other parameters, first step one will be the addendum value. Addendum. So addendum for standard teeth can be found out in the page number 28.5. You can find the formula for addendum. okay, HA is equal to F naught M. So F naught value is also given 1 into 4. okay, see here, so in the formula itself 1 into 4, that is the 4 mm. okay, so next dedendum value. So the dedendum value can be found out by F naught into M plus 1, so that is 1.25 M. okay, okay, that is 5 mm. okay, so the next we have to calculate the tip circle diameter. So the tip circle diameter can be found out by d1 plus 2ha and d2 tip circle diameter, that is d1 plus 2ha. so d1 is 88. okay, 88 plus 2 into ha value is 4. okay, so I will be getting an answer of 96 mm. okay, next tip circle diameter da2. okay, for pinion and gear, one is for pinion and another one is for gear. okay, d2 plus 2ha, so d2 value is 352 plus 2 into ha value is 4. okay, so I have got an answer of 360 mm. okay, next we have to calculate the root circle diameter. So root circle diameter can be found by d1 minus 2hf. hf is nothing but dedendum value. okay, d1 is 88 minus 2 into hf value that we have got is 5. so with that we can find the root circle diameter for pinion and root circle diameter for gear also. okay, so later we have to find out the tooth height factor, tooth height. So tooth height can be found out by h is equal to ha plus hf. okay, so these are the conditions. With that we can close the design procedure for a spur gear. Okay, just try to do all the things one by one, so don't get confused. And we will discuss the problem related to spur gear with respect to height as well as same material. Okay, so these two conditions will be discussed in the next class. Thank you.